Okay, thank you very much for the organizers for the kind invitation. It's a great honor to be here with you, and I would like to tell you a little bit what is happening in Europe, particularly when it comes to the request for exascale and how we prepare applications towards the exascale. You've probably seen this graph before. That's the historic development of the power of supercomputers as captured in the top 500 list, that if you just do a projection, then by magic in the year 2020 an exascale system should appear somewhere. As we know today, it's very unlikely that it will happen by 2020, but 2022, 2025, who knows, in the next couple of years it will happen. We'll see an exaflop system. The question, of course, is, this is all great and there will be one exaflop system in the world. Why should we care? There are a couple of very important applications that will probably need exascale, but most of the science we are doing is still at the terascale, petascale, or even below. And we just heard from the Ministry of Iran that Iran is putting in place to build the petascale system. So this is where most of the science is being done. So shouldn't we just rather care about how to do efficient petascale and terascale and leave those exascale folks alone? Well, the bad news is that these things don't happen in isolation. The technology that is currently being developed for the exascale is pervasive. So whatever you will see on a petascale system in the coming years is the same you see on the exascale system. There is no difference. And the quest and the technology advances, they really show critical problems that we have with our current approach to supercomputing. A key problem we are facing is a problem of power. We've been running into what we call a power wall some 10-15 years ago, where basically we could not scale anymore the frequency of our processors, and thus the easy time of having more powerful processor just by waiting for the next generation has gone. Instead, what happened is that people increased the number of cores that you had on the processors, so-called multi-cores. But now you suddenly have to explicitly deal with parallelism to exploit the efficiency of the processors. And this is continuing for some while. What will be very interesting actually is see the upper line, that's Moore's law, how many transistors you can actually pack on a chip. And this is continuing for a while, but in, I don't know, 5-10 years also that will stop, and that will then be a very interesting time again. But we also have a power problem when we want to scale systems. This picture here, that's our system that we run in Stockholm, called Beskov. That's a system that delivers 1.3 petaflops in peak performance, sustained performance. And it draws 600 kilowatt. So if we just scale this to an exaflop system, we would need 500 megawatt. A megawatt electricity per year gives, give and take, costs €1 million. Nobody will give me 500 million euros, right, to simply power up this machine. If we look at the most powerful efficient systems, like the current top one, the Day3 Laure in China, that delivers 100 petaflops at 15 megawatt. Still, you would need 150 megawatt. So we need to find a way that we can actually build exascale systems without having the need to build a nuclear power plant next to it. The design goal really is to have 20 megawatt or so, yeah, for an exaflop system. Perhaps the early exaflop systems will draw a little bit more, but that's about where people say that's realistic. And in order to get there, we need further advances on all levels of technology. This is a projection that the Department of Energy has been doing, and it basically looked into what is the projected advances of CMOS technologies, what will be the energy draw for current heavyweight like Intel cores and lightweight cores like GPU cores. And this line basically is the target line where we need in terms of energy efficiency, and it's clear that even taking into account CMOS developments, heavyweight cores alone, they will not meet the target. So we will need to go into some machine where we have lots of lightweight cores and perhaps few heavyweight cores. Of course, you can continue with current technology, right? Then you're stuck up somewhere here. So future systems will be very heterogeneous. They will have combinations of big cores, latency optimized cores, that have not a lot of parallelism. That's basically what we see today in the Intel systems. And most of the power will actually be provided by tiny cores, but lots of them. And they will be throughput optimized cores, like NVIDIA GPUs are today. So a combination of those, and actually you see it when you look at the design of the Coral systems that the US is putting in place, you have a combination of these fat cores and thin cores. But it's not only the CPU that is changing, we also see lots of changing in the memory hierarchies. So from our standard model where we have a CPU, memory, storage, and distance storage, and perhaps then of course caches in between, we will see a much deeper memory and I/O hierarchy with high bandwidth memory, NVRAM, SSD storage, and so forth. All that is being put in place not only to increase efficiency but also to save energy, right? So we need to deal with that. So we are really faced now with a new world of computing where increased power only comes through parallelism. We need to deal explicitly with data locality. So data locality will be a critical part. Some people even say flops come for free because you will have lots of flops on those systems. But moving data around, that will be difficult. Computers are heterogeneous and they are dynamic. And of course, fault tolerance may become an issue. So, what does this mean for applications? Well, the good old times have gone where we simply waited for the next generation of CPUs to solve larger problems. So we need to treat parallelism as a first-class problem and not just as an implementation detail that somebody will fix later on. We may need to revisit algorithms because we need to exploit massive parallelism and we need to reduce data movement. And so far people have been focusing on reducing flops, right? And that's probably the wrong target on these new systems. You need to increase parallelism, reduce data movement. We need to look into then how we implement it. What are the programming models that we use to implement those systems? And we need to have a close collaboration in designers of hardware algorithms, programming environments and applications. So, what is Europe doing in order to facilitate this? Europe has put in place what is called a public-private partnership, where the European Commission works together with academia and industry to further the SSK research. There is three components. We have PRAISE, which is putting in place the European high-performance supercomputing infrastructure. We have technology projects in future emerging technology projects, and we have excellent science, which is applications in what we call centers of excellence. And there is some 700 million euros in Horizon 2020, the current funding scheme of the European Commission, that is being spent on those projects for technology advances and applications. And these projects are driven by what is called a strategic research agenda that is being revisited every 2-3 years, that looks into issues like HPC system architecture, system software, programming environments, mathematics, algorithms, the convergence between big data and HPC and so forth. And we had a first wave of projects that actually started 1.5 years ago that looked into different aspects of this. What will be the compute nodes? What will be the interconnect? What will be the memory and storage hierarchy? What are new mathematical concepts, new algorithmic concepts we can use? Do we have the programming tools, the programming environments, and also looking into new usage models like data-intensive and real-time applications. We are now trying to bring together a lot of these developments into what we call extreme scale demonstrators. Extreme scale demonstrators are real systems that should be built taking as much as possible of the new technology that is being developed and showcase that they can actually reach the exascale. So it will be relatively small systems. Still, it will be some 20-30 petaflops with a design target of reaching half an exaflop. And they should be built together by technology providers, European HPC centers, and the application owners. And here comes the bottom line here of this picture of all the projects. We created a new concept which is called Centers of Excellence that have the aim to support European applications on this new class of systems. So they have the target to improve the performance of applications and the scaling of applications to the exascale, provide training and support, so also help the scientists actually to formulate the problems in a way that they can fit, and actually covering the full workflow. Not just the pure simulation, but also looking into how is pre and post processing done, how you deal with your data, and so forth. And then the first wave of Centers of Excellence, the European Commission funded 9 centers that look into various different aspects. We have centers that look into energy research, biomolecular research, materials, weather and climate, performance optimization, global system science, and computational biomedicine. So it's a wide range of different sectors that is covered by the Centers of Excellence. Of course, not the full range of scientific applications, which is a little bit an issue. So what are they trying to do? And I'll give you just a few examples of what's happening. This is the Easy Ways, that's the Center for Climate Research. And the current challenge they have is that they want to actually refine their current models from a 10-kilometer resolutions that they have today to a 1-kilometer resolution. Here you see the performance of the various models as they stand today, going up to 36,000 cores. The target is that they need to have a simulation of about a year per day. So where the blue arrow is 365 forecast days per day, that's their target, right? And with the current model, the 5-kilometer model, is the current research model, they are there. If you look at the current 1.2-kilometer model, that's down here. So they are still at 10 to 18 days. And if you look at the gradient of the lines, the scaling is not very, very nice. So you will not reach the 365 days by just throwing more resources to it. So there's a lot of work needed to make those models more efficient and better scaling. Another example that is more looking into data is a project that deals with material science, and it has the goal to capture the knowledge that is available for the material science simulations in a better way, make them available also for new approaches like machine learning and artificial intelligence and so forth. So they are really trying to create, to capture all the simulations, all the data that is out there, create the knowledge and help advancing material science through that. Another example comes from the life sciences, where we are working on. This is an example for predicting the interactomes by docking, having about 20,000 human proteins, and you want to have an interactome docking, you probably need about 10 billion CPU hours and 100 exabytes of data. So how we deal with that is a big issue. When it comes to molecular dynamics, which is another of the examples that we use to motivate the exascale, here is an example of an ion channel in a nerve cell, and which you need to understand proteins and drugs. And if you want to do a 1 microsecond simulation, you need some 10 exaflops. But then you have different charges that you need to do different combinations. So we are actually approaching a set of flop performance for this application. So what we do in Europe, in order to develop the next version of the strategic research agenda, we're actually going and talking to all these different domains and say, what are your pain points? What are your problems with respect to various different aspects? I'm not going to read through all that. I guess you will get the slides later on so you can have a look. But so we are looking on what would different application domain actually need from a HPC system architecture, system software, programming environment, I/O. What are new usage models? Are there big data models that can be combined with HPC? What are mathematics algorithmic problems that need to be solved? And a few top requirements that it's a very early draft because we're just starting this discussion to come up is clearly the new HPC system architecture that I have described before is a challenge. The applications don't know yet how to actually deal with that, how to efficiently deal with the new memory and I/O hierarchies, how to balance compute and I/O, what will actually be the balance and the characteristics of the new systems. How do you efficiently interact in the heterogeneous world between fat and thin nodes? When it comes to programming environments, clearly dynamic environments are needed. I think Thomas Sterling in his first talk has alluded a bit to that. And when it comes to new hardware technologies, not surprisingly, it's clearly important that they come with standardized interfaces. So you can have a wonderful new interconnect, but if you're not supporting standard protocols, network protocols, applications will not embark and use it. So you need to be able to continue to use your MPI, your OpenCL, your OpenMP, whatever. And I want to give you just a little glimpse in how such a Center of Excellence works, and this is BioXL, the Center of Excellence of Computational Biomolecular Research. It is coordinated by me. And this is a center that looks to life science and HPC. And we know life science, a lot of things have been done in wet labs, but increasingly things are moving into computational science. But the scales we deal in life sciences are huge, right? They're ranging from single atoms to full humans or even full populations. And the methods that are being used are too different that you can actually in one center try to capture all that. So within BioXL, we stay here in the subcellular level, right? Starting from the atomistic level to the subcellular level. And this is essentially biomolecular modeling and simulations that has a lot of different application areas like in neuroinformatics, personalized medicine, drug design, biomarkers design, and so forth. We set up the center on 3 pillars. We want to produce excellent software, so we want to look at common software packages that are being used in the field and make them fit for the exascale. But we also want to make sure that the software is usable. Biomolecular researchers are not HPC nerds, right? They need to have environments, they need to have workflows, they need to have tools that they can work with. So usability becomes a key issue. And then support, consultancy, how to set up your experiments and so forth is very important. So we set up these 3 pillars together with dissemination and training. In the first phase of the project, we are starting to look at 3 different software packages that cover different aspects. We have GROMEX, which is a molecular dynamic simulation system, HALOC, which does integrative modeling of macroassemblies, and CPMD, which is a hybrid QMMM code. So we look at different scales and different computational techniques in here. And let me give you a little example of what are the challenges actually when it comes to molecular dynamics at the exascale. So here you see the different scales going from the physics to really the biology, and we are here now at the microsecond scale, and we want to push things forward into the biology range so that actually proper biological experiments can verify the computational simulation. Of course, we want to be really then in the second range, right? But the current goal is how can we go from microsecond to a millisecond range. And the challenge here is that we need strong scaling. We have time steps of 5 femtoseconds. We need to spend about 200 billion iterations to reach the millisecond. And if we want to spend 100 days for that, then we need each iteration basically to complete in about 40 microseconds, which is not a lot, right? And the problem we have is that we build larger and larger computers which are supposed to be more powerful, right? They are more powerful because you can simulate larger systems. But we are not interested into larger molecules because they are not interesting. We are interested in longer timescales. And these larger systems actually are not designed to help us with that problem, which is an issue. And this is going up and up, right? So we are now in the range of some 100 million cores with the sunlight in China, and we will see then the systems that will have up to 1 billion cores. And we need to start ourselves, how will we use this 1 billion cores? Clearly in molecular dynamics we will not use 1 billion cores by just creating larger molecules, or simulating larger molecules. So the way to exascale for molecular dynamics actually is that we go into ensemble computing. That we use techniques like milestoning, Markov chain models, Monte Carlo sampling, and so forth to actually allow to go to larger timescales, right, with these techniques. So we end up with a very, very difficult and multi-stage parallelization strategy. You have ensembles, large-scale ensembles in your workflow. You do a classical MPI domain decomposition that is then run on a node that, as we said, consists of GPUs and CPUs. And to make things more complicated, of course, on the CPU you also need to exploit the vector units that you have. So this is what we are working on to make this full chain actually work in an efficient way. The other objectives, as I said, is usability. So we work a lot with workflows. We analyze different use cases and try to fill the gaps and build custom-made workflows that allow people to very easily use the large-scale simulations, data sending back and forth in their experiments. And the third objective, as I said, is competence building. So we work with academic, industrial users, help them to train them, make best use of the software and the computational infrastructure. In order to do that, we actually have created a couple of interest groups where actually the community can interact with each other on various topics. And if you're interested in this, please go to our webpage. You can join them. If you are in the US, there is a sister project actually that has just started, the Molecular Science Software Institute, more or less SI, that has similar goals and that also works with software developers and the communities trying to improve the software and the way the software is being used. So, to sum up, the quest for exascale and what is happening on the direction towards the exascale is affecting us all. We cannot simply ignore it. We cannot just say, oh, we run our terascale simulations, we are fine. We don't need to worry about that. Look at what the Minister of Iran has shown before in the design of the upcoming petascale system. I've seen Intel CPUs there, I've seen NVIDIA GPUs there, I've seen nice landing Xeon Phi systems there. Whatever you build today is a very heterogeneous system. You need to spend significant effort at all levels to be ready for the hardware to come. Of course, what will be very interesting, we're still talking classical hardware. We might see even more exotic hardware come. right? The Human Brain Project is looking into neuromorphic hardware that tries to learn from how the human brain works and see whether this can be used for classical computation. That would be a very interesting approach. I hope I've shown you that Europe is investing heavily into exascale technologies, and the centers of excellence are our key point towards supporting the scientific communities on the path towards the exascale. What is needed, of course, here is these are long-term endeavors. The European Commission works with 3 years timescales, which is not really very convenient if you are on a quest that has a horizon of 10-15 years. So long-term commitment is really needed if you want to set something up like this. And you need a critical mass. It needs a lot of effort to solve the exascale issues. Thank you very much.
We have a couple of minutes for 2 questions. Yes, please.
About the first part of the presentation, some countries like China, they focus on using small and cheap processors like mobile processors to make supercomputers instead of making powerful CPUs, because first of all they don't want to maybe rely on some big companies like Intel, and the second one to save the power. And they were very successful in some cases, not on HPC exactly, but at least for cloud services, they were very successful. Like in some cases, they saved 60% power or 50% cost. And I want to see, I want to know now, what future do you see for using mobile processor for supercomputers instead of using?
So this is something that actually Europe also has been looking for quite some years, and you see here the Mont Blanc project, for instance, that was really looking into how can, in their case, ARM processors be used for supercomputers. This is clearly a viable path, and that will be continued, and there is actually a lot of those projects are being based on ARM technology, which is a technology originally developed for mobile phones. It's not the silver bullet though, right? So mobile phones are low power, low energy, because they don't provide much computational power. If you need to provide a lot of computational power, again, energy consumption rises as well. So yes, it's a viable path forward, but we will need to have combinations of many different technologies.
Thank you.
I think Thomas wanted to make a comment.
Yes. Yes, well, I guess I'm leveraging the last question. So I didn't even see Mont Blanc on the screen.
Yeah, it was too short, I guess, yes.
And so I was going to ask you what happened to it. But there's a more pervasive issue. First of all, very interested. Your talk is the most comprehensive talk I've seen to date on the European paths. So thank you very much for your effort in presenting that.
Oh, good. I get to talk about microphone. But honestly, and I'm sure you would concur, there is a gap. There does not seem to be a lot of energy or initiative in the development of new hardware architecture designs within Europe, within the European Union. Correct me if I'm wrong. I hope I am wrong. But rather anticipating and accepting what's handed from the international vendors. And I'd like to ask if that's true, and if so, why?
You're putting your finger on a really, really difficult spot in the current European politics.
Hence the question.
Yes. So there is a huge debate going on at the moment whether Europe should invest in its own microprocessor design, or, as Thomas said, just leverage and participate into what is happening internationally, where internationally in most cases means US, right? And we talk about IBM, Intel, NVIDIA. That's about it, right? The European Commission has recently launched the idea to fund European microprocessor development. that was part of the discussion they had at the 60 years anniversary of the European Union in Rome a couple of weeks ago. So there is supposed to be money for that. How much money, how it will be organized, this is all still very, very nebulous, and I can't really comment on this. But there is discussions to that extent going on. My personal viewpoint on this is that if Europe is going to embark on that, it's very late, which is an issue. And knowing the European Commission, they will put not enough money on it, which is the second issue. So that makes me wonder whether it's worth it or not, right? Because putting a little money on something that comes too late is not going to make you succeed. You need to put a lot of money. Yeah? And if you're late, then you need to put even more money. But we'll see what is happening.
Thank you very much, Dr. Oh, well, okay, short question, please. Yes, we run out of time.
If I'm not right, I believe, for example, EasyWays in Europe has started investing on DSL programming languages, if I'm not wrong, at least in one of the projects. To what extent do you believe that DSL would be an answer to the scientific programming? And perhaps the other question that might be relevant, to what extent do you think doing a specific hardware would be an answer to our concern in the future?
So I'm not an expert in DSL, I have to say. I know that several communities are experimenting with this, and it probably has its role in a very specific communities. It will help to build higher level frameworks for them. But I cannot really comment on this because that's not my field of expertise. When it comes to domain-specific hardware, we've seen this, for instance, in the field of molecular dynamics that I was describing with the Anton machine, right, which was a big endeavor to build a very efficient, dedicated hardware. How many Antons do you see in the world? We are hit by economical problems, right? We don't have communities that are strong enough on a large scale to justify the heavy investment in dedicated hardware for them. I think dedicated hardware clearly works, but we will end up with the usual compromise that we have, where we need to fit different usage models on one machine, and we will make a compromise. Because these machines are too expensive. You will see one exascale machine, right, initially. You will not see an exascale machine for fluid dynamics and another one for molecular dynamics. Unless we find good donors, who knows?
Thank you very much. Now I'm going to invite Professor Voevodi to present his presentation for 25 minutes and 5 minutes for questions, please.